So what you'll see labeled in front of you are the various transformations that we can see for a trig function. And so we'll just go through what each of those transformations are and how we can use them, and just to remind ourselves of what they are. So that a value out in front is our vertical stretch by a factor of a. And we also see it as a reflection in our x-axis. Our k value is our horizontal stretch by a factor of 1 over k. You'll recall that our horizontal is opposite of how we read it. Our c is a horizontal shift, and d is a vertical shift up or down. You'll notice that I have not included in here where k is less than 0, so where there is a reflection across the y-axis, because we'll notice that our curves that we're using are periodic, so they will repeat themselves over and over. Okay, so those are your key transformations, but we can also take information from those transformations. So you'll notice beside our a, we know that it's a vertical stretch by a factor of a, but we also know that the absolute value of a, so when we take the absolute value, we're talking about it as it's the positive amount. So the absolute value of a is known as our amplitude. And you'll recall that our amplitude is half the height. So at times you might have talked about it as our max minus our min divided by 2, right? If I take the highest point, I subtract my lowest point, and I divide it by 2, I get half the height, right? So not something that we need to memorize, but we don't need to remember that formula if we think about it just as half the height. You'll recall we have an amplitude for our sine and cos curves, but we do not have an amplitude for our tan curve. So we can have a vertical stretch for our tan curve, but we do not state it in terms of an amplitude because our tan curve continues to go forever to positive infinity and forever to negative infinity. It does not have a maximum or minimum value. We have our horizontal stretch by a factor of 1 over k. And you'll recall from our previous lesson, we have our little friendly formula that's period equals 2 pi divided by k. So that can help us to confirm the period of our function. So how long does it take for one cycle to occur? Our horizontal shift, when we're starting to talk in terms of trig functions, we refer to that as a phase shift. And our vertical shift, if we're shifting our graph up or down, if you think of your base sine curve and your base cos curve, it starts the middle of those graphs vertically, have a height of 0. The middle of our graph is 0. So if we shift that curve up or we shift that curve down, our middle of our curve should still be shifted up or down depending on what d is. So our y equals d is that middle part of our graph, okay? So we can call it, it's often called the equation of the sinusoidal axes, but we often just call it the equation of the axes. So that's our reference point to it. So for example, if I have my sine curve, we notice that my equation of my axes is at y equals 0. And if I were to shift this graph up 3 units, every part of my curve would be shifted up 3 units. So the middle part of my graph would still be, I would have that horizontal at y equals 3. So that piece of information, that y equals d, is really helpful to us when thinking about where is the middle of my curve. So those are the key pieces of information that we have that we can tell just by looking at our equation. Okay, on your next line, what we're going to be asking you to do. So when we're going to sketch, you'll notice I'm asking you for the first positive cycle. Okay, so I'm always going to be asking you for the first positive cycle of cos and our first positive cycle of sine. So on our first graph, just sketch for me your first positive cycle of sine. So I know I start at 0, 0. So I'm going to label my y-intercept, the location of my maximum. I do not like how that curve looks. And the location of my minimum. So this is some of the key information that you will be labeling for me. We will be labeling our y-intercept, our minimum, and our maximum values. So just how when we sketched our our log functions and our exponential functions, you had some key pieces of information that you needed to include on each of those graphs. Same thing here. We want our y-intercept, our minimum, and our maximum. But if your y-intercept is also your maximum, we're going to have to label another point as well. Sorry, I really don't like the look of that sine cos curve. Okay. So I have my y-intercept's 1, my minimum is at pi and negative 1, and since my y-intercept is also my maximum, I'm going to have to label another maximum, which would be at 2 pi and 1. So again, what we're going to be using for our curves moving forward, y-intercept, our maximum, and our minimum. If your max or min happens to be your y-intercept, you need another point, so the next max or min. And we will be sketching these for the first positive cycle. Okay, so that's what we are looking at when we're progressing for these curves. Okay, so I have all of that information listed here. Okay, your approximate y-intercept is fine. Ideally, if it's an exact one, we're going to leave it as exact. 1 maximum point, 1 minimum point. So we need to make sure that we have 3 points are labeled on each sketch. We have a couple of different strategies to help us with this. Oops. We can start with the equation of the axes. Or we can look at our max and min and deal with horizontal and vertical transformations. I personally like to use a combination of the two. So I'm going to show you a few different strategies of how we can sketch these. At times, I'll start with the equation of the axes, and at other times, I will start with my horizontal and vertical transformations. So we will go through those together, and then you can build from there some strategies that work well for you. Okay, so our first function that we've been given is y equals 3 sine 2x minus 4. So I have a few things happening here. I know I have a vertical stretch by a factor of 3. I know my amplitude is 3, so half my height is 3. I have a horizontal stretch by a factor of a half. So already that's telling me about my x values, that my period has been cut in half. And I know that I have a shift down 4 units, which tells me that my equation of my axes has been shifted down 4. So that middle of my graph, what's happening horizontally is that it's going to be at a negative 4, will be the middle of that graph. Okay, so how do we go about getting all of this information to help us out? So let's start. So one option is let's start with our equation of the axes. Okay, so I know my equation of the axes, the middle of my graph is going to be at y equals negative 4. My amplitude is 3. So if that's half my height, I know that I'm going to go up 3 from my middle will get me to my maximum. So if I go up 3 from my middle to get me to my maximum, negative 4 plus 3, give me a y value of negative 1. And I have to go down 3 to get to my minimum. So just using the information I know about my equation of the axes and my amplitude, I was able to find out the y values of my max and my minimum. We need to also know what's happening to our x coordinates as well. So we need to know what's happening horizontally. So we have a horizontal stretch by a factor of a half. So they're half the distance. So if we know that the max normally, so we have a horizontal stretch by a factor of 1/2. So again, we're cutting them in half. So if our max used to have a location, so think of your base sine curve, it used to have a location at pi by 2. I'm going to cut that in half, and now my max occurs at pi by 4. My minimum used to occur at 3 pi by 2. I cut that in half, and now it's at 3 pi by 4. Okay, so that's how we can find our values of x. So again, I'm hoping you'll notice just right away from looking at the equation, we dealt with the vertical, and I dealt with my equation of the axes, that -4, that vertical shift down -4, and then I added my amplitude to the top to that to get my max, and I subtracted it to get my min. We then had to look at what's happening to our x coordinates, and we know that there's a horizontal stretch by a factor of a half. I'm going to just show for you, and I'm going to put it in, I'll change up the color, orange here, just a few checks. What are some checks that you could do to make sure that you had this down? So our period, we know from our little trusty equation that it's 2 pi by k. Our k value is 2. This value here is our k value. So we know that the period of this function would be 2 pi divided by 2, which is pi. So it should only take pi units to go through a full rotation. But we can also double check that we have calculated these x values of our max and our min correctly. Okay, so I can do that. If I know the distance between my max and my min is half of a rotation, then I know that they should occur now in pi by 2 units, right? So I can take my 3 pi by 4 and I can subtract my pi by 4, get 2 pi by 4, which equals pi by 2. Pi by 2 is half the period. So that means it takes half the period to get from my max to our min, which is what we know occurs on all of our curves, for our base curves for sine and cos. To get from our max to our min is a half rotation. It's half the period. And what you'll notice here, if our period of this function is now pi, I can do a quick check for my horizontal and I realize it takes pi by 2 to get from my max to my min. So what I have there in orange are just additional checks that you can do for yourself. I do not need to see that work written there. All right. The last thing, let's double check our y-intercept. We can let x equal to 0. Now I'm hoping the fact that we have not shifted this left or right does already tell us what our x value should be. So sine of 0 is 0. So 3 times 0 minus 4. So we know that our y-intercept is a -4, which again, sine starts on the y-intercept. And since we have not shifted this left or right, our y-intercept should still remain on the y-axis. Okay, so now last thing is to sketch this. So we know we're at a minus 4. We have not reflected, so I know sine is still starting at my y-intercept. And oops, and it's increasing. So we start at our y-intercept. Sorry. Oh my gosh. Okay. So we've started at our y-intercept and we've increased. So we know that this is a pi by 4 and -1. Our minimum was at 3 pi by 4 and -7. And our y-intercept was at a -4. So there would be your graph. You do not have to include these extra little points that I had here. Awesome. So there would be our full rotation. Something to be aware of, which I'm going to draw this on for this example, but we should not be including it on our graph. We could draw, so if I put my equation of my axes on here, I can use that as a quick check, just as I become more comfortable, that is the distance between my equation of the axes to my max that I'm in. Vertically, have I drawn that around the same distance, just to get a sense of what my curve looks like. Now, again, that's something that we can picture. We do not want to include the equation of the axes on your graph, because I think we'll all recall, what does a dotted line on our curve represent? It represents an asymptote. And there is no horizontal asymptote here for our sine curve. So do not include your equation of your asymptote in any of your final sketches for me. You can be thinking about it, and by all means use that to think about how is my curve? Did I get my distances? Are they pretty accurate? What does that look like? Okay. So we should be aware, we can be aware of that equation of our axes, but we should not be including it on our graph. Okay, so when we look at example B, we notice a few things. We notice we have a reflection across the x-axis. We have a horizontal stretch by a factor of 1/3. We have a phase shift to the left pi by 6. And we have a vertical shift up 1 unit. So first, let's start to think about what we have here. So our equation of our axes, we have y is equal to 1. We notice that our a value, our amplitude, would be a 1. So I'm going to add 1 to get my max and subtract 1 to get my min. So I should be able to calculate that I have a max with a y value of 2 and a min with a y value of 0. So now we need to look at what's happening with our x values. So if you think about your original coast curve, we start at a maximum of 0 and 1. Well, if we're shifting it to the left pi by 6, we have now shifted that pi by 6 out of our first rotation. So we want to think about what is our next maximum. And our next maximum occurs at 2 pi. So let's work from 2 pi. So if I take 2 pi, I'm horizontally stretching it by a factor of 1/3, which means I'm dividing it by 3. And then I'm shifting it to the left pi by 6. Get my common denominator. And we calculate that our max is at an x value of pi by 2. And I'm going to say if that's what we've calculated, then we've fallen into a trap. But it's easy to fix. The trap that we fell into is we did not take into account this reflection. So what used to be at a maximum is now at our minimum. Okay, so but really, this is our minimum. So we have a minimum at pi by 2 and 0. So what used to be a maximum is now a minimum. So we've adjusted, we noticed the trap that we kind of fell into, and now we've made some adjustments. So since reflecting, where does our minimum normally occur? So what used to be our minimum, so we know our minimum used to occur at pi. We're going to horizontally stretch that by a factor of 1/3, which means I'm dividing by 3, shifting it to the left, pi by 6, and we get our common denominator. We calculate that that is at pi by 6. So after these transformations, our max is at pi by 6. So we can do a few of our checks just to make sure. We know that our period is 2 pi by k, and our k value is 3. So we know that it will take 2 pi by 3 for one cycle of this function to occur. And then we can double check the horizontal distance between the max and the min should be half of our period. And we know that if our minimum is at pi by 2, we subtract our max, we are going to get pi by 3. So half of our period is equal to pi by 3, so that we can be confident in our max and min values for x, because the distance between them is half of the distance of our period. And then lastly, let's double check our y-intercept. So our y-intercept, I'm going to let x equal to 0. I can simplify my angle so that I have it written as cos of pi by 2. And we know that cos of pi by 2 is equal to 0. So we can use that thinking about our base cos curve, or we can think about it on our axes where our terminal arm would be. And so we find out that our y-intercept is 1. I'm hoping we'll notice a few things here when we go to sketch this. We know that our equation of our axes is 1, but we also notice that our y-intercept is 1. So our first positive rotation does actually start at the equation of our axes, and because our curve was reflected, we're actually going to hit our maximum before hitting that minimum and then returning to the equation of our axes. And so I should have pi by 6 and 2, and pi by 2 and 0. Again, noticing the distance between that max and the equation of the axes should be half of the distance from my max to my min. And so the point I'm hoping that you're recognizing about why did I give you this particular question, it was to focus on that reflection and the impact that it can have on our curve. So this question here, you'll notice, has almost every transformation that you could possibly see in it. We have a vertical stretch, we have a horizontal stretch, we have a phase shift, and we have a shift up. The only thing we do not have is a reflection across that x-axis. And again, you'll recall in our last example, it was when we reflected across the x-axis that we had to be mindful of what was a max was now a min, and what was a min is now a max. But we do not have to worry about that in this function. So let's think about what we have. So let's deal with our vertical first. I have my equation of my axes is at 4. So I know if my equation of my axes is at 4, and my amplitude is 0.5, to get to my max, I'm going to have to add 0.5. To get to my min, I'm going to have to subtract 0.5. So I have my max, and I have my min. So very quickly, vertically, I can determine that I have a maximum value of 4.5 and I have a minimum value of 3.5. Now we have to think about what's happening with our horizontal. So we have a horizontal stretch by a factor of 3, and then we are shifting it to the right pi by 2. So if we think about our sine curve, our max used to be at pi by 2, a horizontal stretch by a factor of 3, so I'm going to multiply it by 3, and then I have to shift it to the right pi by 2. And what we notice, 3 pi by 2 plus pi by 2 gives me 4 pi by 2, which gives me a value of 2 pi. So my maximum is at 2 pi and 4 pi by 6. My minimum, if I think about my minimum curve on sine, my minimum was located at a 3 pi by 2. Horizontally stretch that by a factor of 3. And then I add pi by 2 to it. So I'm going to be at 9 pi by 2 plus pi by 2 gives me 10 pi by 2, which will give me 5 pi. So my minimum is at a 5 pi and 3 pi by 2. My y-intercept, I'm going to let x equal to 0. I know the location of sine negative pi by 6. Just means I am dropping that terminal arm. Across from my smallest angle is my smallest side length. So I'm going to have a negative quarter plus 4, which should give me 15 quarters. So I will have a y-intercept of 15 quarters. And lastly, I can do that little quick check that we've been doing if I'm wanting to double check. So I know my period is equal to 2 pi over k. So that means my k value is 1/3, which means my period should be 6 pi. So the distance horizontally between my max and my min should be 3 pi. Which we notice, if we look at those values, if one's at 2 pi and the other one's at 5 pi, then we should know that the horizontal distance between our max and our min is 3 pi. So now when we go to sketch this, a few things I want us to consider. We know that our equation of the axes is at 4. We know our y-intercept is at 15 quarters. So our y-intercept is just slightly below that equation of the axes. So I am going to have to curve up a bit before I can continue on with my sine curve. And then I come down. And I want to be making sure I'm finishing off where it would connect here. So I notice I have my 2 pi and 9/2. I have my 5 pi and 7/2. And you'll notice, again, this little piece here should be finishing off at the end. It should be continuous, right? It's a periodic function, so that extra little piece that we see should be continuing on with our graph. Okay? So that's how we can ensure that we've shown that first positive rotation, and just being mindful of those scales. And so again, what this means is we should be ending a bit less than 4. So our graph should be ending a bit less than 4, because again, we started at a bit less than 4. So in order to have that full 1 rotation where one graph ends, we should see it continue at the beginning. Okay, so let's first begin with our base tan function. So we know that tan is opposite over adjacent. So we know that the adjacent side does not exist at 0 at pi by 2 and 3 pi by 2 because our adjacent side at those spots are 0. So we recall from our previous lesson that that means we have asymptotes at pi by 2 and 3 pi by 2. We also know that when it's at 0, our adjacent side is 0. Sorry, our opposite side is 0 here at 0 and 2 pi. So our opposite side is 0 at 0, pi, and 2 pi. So we know on our curve we have a y value of 0. And then we talked about, well, instead of getting into the nitty-gritty of the decimal approximations for pi by 6 and pi by 3s, let's think about our curve. And we go at pi by 4, I have a y value of 1. Because we know on our pi by 4, we have a y value of 1. I know that tan is positive in my first quadrant. As I rotate into my second quadrant, my opposite side is positive, my adjacent side is negative. So a positive and a negative give me a negative. So I know as I rotate into that second quadrant, I'm going to have a y value of a negative 1. So at 3 pi by 4, I have a y value of a negative 1. As I rotate into my third quadrant, my opposite side and my adjacent side are both negative, so two negatives make a positive. So as I've rotated, at 5 pi by 4, I know I'm at a positive 1. And then as I continue to rotate again, in quadrant 4, my opposite side is negative, my adjacent side is positive, a negative and a positive provide a negative 1. And so again, we can use those key values. We know we continue to get closer and closer to that asymptote. The other thing I'm hoping we recall is that we know tan repeats every pi units. So I also could have recognized, okay, if this is where I have a y value of negative 1, pi units later, or according to our grids, right, 1, 2, 3, 4, 5, 6 grid lines later, I'm going to have that same y value of a negative 1, right? So once we know what one of our tan curves look like, we can just continue to repeat that pattern because, again, it's periodic. So in orange, let's keep our orange as our base function. I do not need to see the graph of your base function, but I want us to picture it. And for this first example, I think it's important that we draw it on to help us. But you are not responsible for drawing me the curve of your base function. So I just want to make sure we're okay with that. Okay, so let's apply our transformation. So let's first start at 0, 0. Vertically stretch 0, 0 by a factor of 2. I've reflect it, still going to be at 0. Shift it to the right, pi by 3, which we know is 2 grid lines, and up 1. So we've transformed that point of 0, 0 after applying our transformations. So now let's go to pi by 4 and 1. Vertically stretch that by a factor of 2. Reflect it, it's going to be at a negative 2. Shift it to the right, pi by 3, and up 1. Same thing with our asymptote. A vertical stretch and a reflection is not going to affect our asymptote. So we can shift it to the right, pi by 3, and again, shifting it up 1 is not going to affect it because it's always going to forever to infinity and negative infinity. Okay, so let's continue on. So let's go 3 pi by 4 and negative 1. Vertical stretch by a factor of 2. Reflect, shift to the right, pi by 3, and up 1. And then at pi and 0, vertically stretched by a factor of 2. Reflect is still going to be at a y value of 0. shift to the right pi by 3, and up 1. And then again, we can continue this pattern. I'm at now 5 pi by 4 and 1, vertically stretched by a factor of 2. Reflect, shift to the right pi by 3 and up 1. And lastly, same thing, we can adjust our asymptote by shifting it to the right pi by 3. So now when I go to connect these, oops, a few things I will notice. One, I'll notice that I still have a period of pi because I have not horizontally stretched this. Now also notice once I had that first rotation, I could have just mapped out my next cycle of pi just by counting squares and our units. So I could have gone over 1.5 and down 2. You'll notice same thing here. I could have gone over 1.5 units and down 2 would have gotten me to that next value from my y value of 1. So again, just a few reminders that they are periodic, and once we know what one cycle is, we can use that information to help us. The next thing we have to be mindful of is that y-intercept. And I'm hoping we recognize that what happens at our y-intercept here would also have an impact here. So I can find out what is happening at 2 pi or what is happening at my y-intercept, because I need to know, is there a portion of my graph that should be showing up here from 11 pi by 6 to 2 pi? And if that's the case, should I be having a value here, a y-intercept, that is showing up within my scale? So let's go ahead and calculate what that y-intercept is. So I can let my y-intercept, let x equal to 0. I know that that's one of my special triangles, so I'm going to drop the terminal arm for my negative pi by 3. And I know tan is opposite over adjacent, so I'll have negative 2. So tan of negative pi by 3 gives me a ratio of negative root 3 plus 1. So really we have a positive 2 root 3 plus 1, which at that point we could type into our calculator just to see what our approximate would be, and we find out that it's approximately 4.46 units. So what I can tell from my scale here is if I go up 2, 3, I am not going to see that cross through my y-intercept, which tells me I am not also going to have a connecting point there at 2 pi. So I know that there is no portion of my graph that will fit within this section. However, if there had been, then I need to make sure that it is continuous so that I continue to see all possible parts of my graph that fit for tan from 0 to 2 pi. So again, we're filling in, as soon as we're given our grid, we're filling in every portion that we can see from 0 to 2 pi for that scale that we are given. And since I do not have a y-intercept that shows within the scale, and that would not continue through because of the function I've been given, that would be our sketch of our transformed function. So again, for your sine and cos curves, you are now drawing them on an axis. You are drawing the first positive rotation, giving me your max, your min, and your y-intercept. And for tan, we are filling in whatever portion of our graph of tan that fits from 0 to 2 pi. So you have some practice questions that you can work on, and let me know if you have any questions.